Today's lecture is on boundary layers. So you might ask, why should we care about boundary layers? And a very easy reason is that we live in one and you'll spend most of your life within one. So a boundary layer is what happens when fluid meets a solid at high velocity. So on an atmospheric scale flow, so a planet scale flow, there's a thing called an atmospheric boundary layer. And that's basically what we live in, and most of our mechanical devices have to deal with the winds and turbulence generated by the atmospheric boundary layer. So this is a very big topic in wind engineering. That's just kind of one type of boundary layer. It's a specific case of a boundary layer, but boundary layers in general apply almost always when a viscous fluid meets a surface. So that's what we're going to learn about today. Just before I do that, the key points from last lecture. So last lecture we talked about strain rate. So strain rate is in fluids we care about the rate of strain because fluids deform continuously. So you can't really define an exact magnitude of strain. The rate of strain, so how fast they're straining in time, is what's important in fluids. And viscosity tells us how a given shear stress that we apply to a fluid element produces a given strain rate. So if you apply a certain shear stress, depending on whether the fluid is Newtonian or non-Newtonian, you'll produce a given strain rate. So a given basically rate of change of deformation of a fluid element. This produces very important effects at walls. So I've put a wall in quotes there. A wall in fluid mechanics just means a solid surface. So when you're analyzing a fluid, a wall is something that fluid sticks to. So that's kind of what a wall means. So in the case we did last time, we did that Couette flow between two plates. So both of those plates would be considered walls, and one of the walls is moving. So the no-slip condition creates shear stress on the wall. You can think of this as the fluid elements that are sticking to the wall by the no-slip condition are being sheared quite a bit because they stick to the wall on one side. On one side, the fluid element sticks to the wall. On the other side, the rest of the fluid kind of pulls on it. And it transfers that shear stress into the wall and creates viscous drag, which is a significant source of drag for many vehicles. So that special case we studied last time has other interesting properties. So its laminar Couette flow between two plates leads to a linear velocity profile. So since the velocity profile is linear, du dy is a constant, which means that the shear stress is constant throughout the fluid. So it's easy to compute the shear stress on the wall in that case, because it's just the same shear stress that's constant throughout the rest of our fluid. Today we're going to extend that kind of idea of fluid sticking to a wall, but to a much more general case. So today's lecture is on boundary layers. We're coming to the end of module 2, but boundary layers are caused by viscosity and they produce a force in fluid motion. So the learning objectives, we want to understand the physical mechanism that produces boundary layers, so why they're actually produced. We want to figure out how we define the thickness of a boundary layer and estimate whether the boundary layer at a given location is going to be a laminar or turbulent boundary layer. We'll talk about the differences between those two types of boundary layers. This will also enable us to compute the actual thickness of a boundary layer, compute something called a skin friction coefficient. The skin friction coefficient is a non-dimensional wall shear stress. So that non-dimensional wall shear stress will allow us to compute a viscous drag force on a flat plate, which is kind of the culmination of boundary layer theory as applied to most, vehicle aerodynamics, that sort of thing. So we can start our notes. So first off, we want to understand the physical mechanism that produces boundary layers. So we'll start off by recalling that shear stress relation. Tau is mu du dy, which maybe any volunteers to tell me, is this a Newtonian or non-Newtonian fluid, if that's the shear stress relation? Any answers? Just take a guess. It's 50-50. Newtonian or non-Newtonian fluid, if that is our shear stress relation? Yes, please. Newtonian, correct. Because there's a linear relationship between shear stress, tau, and the rate of strain du dy. We're going to assume Newtonian fluids most of the time in this class. So this relationship tells us that viscous shear stresses are highest in regions with large velocity gradients. So if there's a large rate of change in the velocity, that produces a large viscous shear stress in our fluid. So one particular region where this happens in our flow is at a no-slip wall. I'm going to draw kind of a stack of fluid parcels here moving towards a wall. Let's say I have these 4 fluid parcels, and they all have the same uniform velocity. So they all have the same velocity. So this is called, say, a uniform flow. That uniform flow is going to be introduced to a wall here that's parallel with the flow. So what happens now when this flow hits the wall is the parcel at the very bottom, the parcel attached to the wall will stick, and it will apply a viscous shear stress on the next parcel, which will slow that parcel down. So the top parcels, say, haven't experienced that slowing down yet. Sorry. The top parcels, they haven't really felt the effect of the wall yet. But as this stack of parcels moves along the wall, that shearing is basically transmitted further and further into the fluid. So I'm drawing the parcel on the wall has 0 velocity because by the no-slip condition. So that one has, the second parcel has slowed down the third one now, and so on. So what's happening here is that there's basically a shear that's being applied. Since the parcels are moving relative to each other, that creates a viscous shear stress that's being applied between the parcels. And like I said, since is mu du dy, the highest velocity gradient will produce the highest shear stress. The velocity gradients are the largest on the parcel at the y, at the parcel at the wall. So that parcel at the wall has the highest shear stress. So now I don't want to have to draw the fluid parcels every time, so I'm going to draw more of a profile of velocity along the wall. So this is kind of the same wall, but now I'm going to draw more of a profile. So coming into the wall, we have this uniform flow. We're going to call that U infinity. When fluid hits the wall here, we have something like this. And something like that. Something like that. So that these lines here are kind of the edge of the profile. So the arrow should really right to there. So the velocity profile, because the parcels keep slowing each other down, the velocity profile will slowly lose momentum due to the viscous effect on the surface. So always far away from the boundary layer, the flow is still at u infinity. So that u infinity is still achieved by the parcels very far from the wall that haven't felt the effects of the wall. But the parcels near the wall certainly feel those effects. And they're slowed down, they slow each other down, then they slow the next ones down, and so on and so on. So we get kind of a growth of a layer of fluid called the boundary layer. So the coordinate system here will be x and y. So that red line is kind of our boundary layer thickness, so to speak. The thickness of that, we notate that by delta x. So delta x is the thickness of the boundary layer. Okay, so we have uniform flow. It hits a plate. It starts slowing down near the plate wall, and that profile gradually, it has a very high gradient rate at the edge of the plate. Then as those parcels slow each other down, it sort of keeps, it keeps becoming more and more gradual. And as it does that, the boundary layer thickness grows. So let's pretend that we're kind of the first people to realize this about boundary layers. Does anyone have an idea about how we would define the thickness of a boundary layer? How could you define that thickness? We only have basically two variables in this problem right now, right? We have some thickness we want to define and u infinity. Does anyone have a guess or an idea of how that boundary layer thickness would be defined? Yes, please.
A certain point when the slope of like the difference reaches a certain value.
Yeah, so the slope of this boundary layer is like, the slope along this is like this, right?
Yeah.
When that reaches a certain value, right? So we could pick, say, like this. We could say the slope here is like that, right? Okay, that's a good idea. Any other questions, or someone want to build on that? Yes, please.
You can check the velocity and say this is 99%.
Very specific answer. We could check the velocity at a given point in the profile. We say, well, the velocity there is going to be some fraction of u infinity, because we know we go from 0 at the wall up to u infinity. So if we say the boundary layer is always at some number, some fraction of u infinity, then we could define the boundary layer thickness like that. And I believe that would actually be equivalent to the slope thing. So the slope basically at u infinity is a straight line. So the slope at 99% of u infinity would be basically a straight line. And that's the most simplest definition of the thickness of this region in space is exactly what she said. So it's going to be a certain constant times u infinity. So delta is a function of x, right? That thickness increases as we move along x. The thickness is defined as zero 0.99 u infinity. Yeah. So when the velocity reaches 99% of u infinity, we're basically out into what's called the free stream. We're far enough away from the wall that we're not really feeling the effects of the wall anymore. So we're 99% of the way to u infinity. So that's kind of at the point where we stop feeling those viscous effects. That's where we say we're out of the boundary layer. So boundary layer thickness, 99%. So specifically, u here is a function of I. So we'll say for a given x U is a U of y. So we're going to look along the y-axis of this profile. So our profile looks something like this. So that is going to be U infinity. Basically what this profile asymptotically approaches. U infinity again is the stream velocity is what it's called. And it's the velocity of this uniform flow before it hits the plate. So that U infinity at the very top of this profile, if you just keep going, eventually you'll be back at U infinity. The wall hasn't affected the flow yet. So if you say you're at 99% U infinity, I'll exaggerate that. So that would be some point here along the profile, some y location has a velocity that's 99% to U infinity, and that y location is going to be delta. So we say the boundary layer is that thick. Are there any questions on that definition of boundary layer thickness? Okay, so let's talk now about laminar and turbulent boundary layers. We need to define a few quantities before we start talking about this. So first we're going to define something called the local Reynolds number. That's defined as follows. So the local Reynolds number is the density rho times U infinity, which is again the velocity very far away from this plate, times x, which is our location along that developing flow. So x is defined here as the location from the leading edge of this plate. So x is like that. So it's rho times U infinity times x over mu, and mu is the dynamic viscosity, which we saw before. So this is a non-dimensional quantity, and this relationship holds true. So for a fixed x location, higher Reynolds number means a thinner boundary. So this is some sort of non-dimensional quantity that we're going to use to characterize boundary layers. So if we fix x and say we're at a given location along the plate, what do you think is one way that we could make Reynolds number higher here? So we're fixing x. Any ideas? It's not a trick question. So if we fix x, if we're going to say we're at a given location in a boundary layer, say we're here, that's our x. Our boundary layer thickness is going to depend on the Reynolds number. So how can we change the Reynolds? Yes. Yes. We could do a fluid of a different density. For example, if we say, oh, we're not in air anymore, we're in water, we'll get a very different boundary layer thickness. We can increase U infinity. So if the flow is going faster over this plate, at a given location, the boundary layer will be thinner. You can also change viscosity. We're going to talk about Reynolds number lots in this course. This is one specific definition of Reynolds number. It's called the local Reynolds number, and it's RE of x there. It's really a function of our position along the plate. So that's one non-dimensional thing we're going to look at. The second one is skin friction coefficient. So tau wall, I'll notate that as tau W, is mu du dy evaluated at the wall. Okay. So the wall shear stress, right, the shear stress that the fluid element on the wall feels is mu du dy, and du dy should be evaluated at the same position of that fluid element. So that's at the wall. So this is a dimensional number. It's like tau is a stress, so it is units of pascals. So tau is a dimensional number. We're going to see in the next module of the course that we sometimes like to work in terms of non-dimensional numbers. So we're going to define a skin friction coefficient. Cf is that tau wall, and we non-dimensionalize this by 1/2 rho u infinity squared. 1/2 is just a convention. So this is skin friction coefficient. You can think of this as like a non-dimensional wall shear stress. So if you know your free stream properties, if you know the velocity far away from this plate and the density, then you can dimensionalize this. So we should study this, the behavior of these non-dimensional numbers. Are there any questions about the definition of these two non-dimensional numbers? So for a smooth, flat plate, we're going to get the following relation. So this is going to be a plot of boundary layer thickness, delta x, which we've defined above, versus the Reynolds number of x. So if we fix Reynolds number of x, just to remind us, is rho u infinity x over mu. Okay, so if we have fixed free stream properties and fixed, we're not going to change anything. We're going to fix everything. We'll see that the boundary layer just grows along x. So if x is the only variable, the boundary layer is just going to keep growing. Here's what we get. So there's a certain profile here. Okay. So that is laminar, a laminar boundary layer. And for this smooth flat plate, the laminar boundary layer continues to grow up to a Reynolds number of about 10 to the 5. So that's the x-coordinate where we can't really assume the boundary layer is going to be laminar anymore. So what is a laminar boundary layer? Remember we talked about laminar and turbulent flow? Turbulent flow has lots of mixing, eddies, that sort of thing. Laminar is the opposite, where things are really smooth. So you get this smooth sort of growth of this boundary layer when it's laminar. That laminar boundary layer growth continues up to about a Reynolds number of 10 to the 5. Then there's some sort of transition region. This is a very complex physical phenomena past the growth of the laminar boundary layer. So the transition region, we're really just not going to worry about it in this course because it's an area of active research in fluid mechanics. So I'm just going to put a question mark there. We do know what happens though when it stop transitioning from laminar to turbulent. We know we get a fully turbulent boundary layer. There. So the fully turbulent boundary layer, I'll show a video, but it is a very erratic version of this boundary layer. So even below that boundary layer height of 99% U infinity, you get all the turbulent motions. We're going to give some relations here for these three types of boundary layers. So it's going to be sort of a table. Oh, sorry, I'll give the Reynolds number here. So for a very smooth flat plate, the transition region ends at about a Reynolds number of 3 million. So past that point, you can assume fully turbulent boundary layer. Okay, so the relations we have, first one is delta of x. So that's the boundary layer thickness. We saw that before. Skin friction coefficient, which because, okay, the definition of skin friction coefficient is here. Skin friction coefficient is tau wall over 1/2 rho u infinity squared. So tau wall is a local quantity, right? So because du dy wall, the slope at the wall changes along this developing boundary layer. So skin friction coefficient is a function of x along our developing boundary layer. Du dy at the wall, because that changes, and the viscous force. So I'm going to give some expressions here for these different quantities. So for a laminar boundary layer, the boundary layer thickness, delta, which is a function of x, is 4.91 x over the Reynolds number at that x location to the 1/2. Skin friction coefficient, 0.664 over the Reynolds number at that location, again to the power of 1/2. Laminar boundary layers are characterized by a low velocity gradient at the wall. So that just says low. Because there's lower velocity gradients, can someone help me? What do we expect the viscous forces to do at the wall? What do we expect for the wall viscous force? So low velocity gradients produce what? I'll give you a choice. It's either high or low. Yes, below. What makes you say higher? So for a fluid, we don't really have static friction. So the viscous force is related to the shear stress, right? The shear stress is mu times the velocity gradient at the wall. So at the start of the lecture, I said viscous shear stresses are highest in regions with high velocity gradients. So do you have a, I guess, do you want to change your answer, or are you still happy with that? This, it's going to be low, right? Yeah. So because we have low, again, the viscous shear forces, they just depend on the velocity gradient. So if we have low velocity gradient, we don't have a lot of viscous forces. This is the behavior we get for a laminar boundary layer. For a turbulent boundary layer, we get the following relations. So delta of x, 0.16x over the Reynolds number to the power of 1/7. Skin friction coefficient is 0.027 over Reynolds number of x to the 1/7. Turbulent boundary layers are characterized by high velocity gradients. The reason that the velocity gradient is high in a turbulent boundary layer is there's lots of mixing. So versus the laminar one just kind of gets more and more gradual and smooth. Once turbulence happens and you get that mixing in the boundary layer, all kind of bets are off about the growth of that profile. It ends up being a very high velocity gradient near the surface. So that leads us to, yes, please, you have a question?
Are these seemingly random numbers like empirical, or are they somehow derived?
That's a good question. So the question is, what are all these random numbers basically? For the laminar case, these are derived analytically. So these are exact values given to 3 significant figures. For the turbulent case, all of these numbers, including basically the transition region, the Reynolds number at which that happens, have a big asterisk that they change a lot depending on the geometry. So this is a super complex phenomenon. So these numbers are here for a smooth flat plate. As soon as you have this kind of assumes like a natural transition to turbulence along a very smooth flat plate. But even if your flat plate is very, very, very smooth, you can get different numbers here. So these are kind of just rough benchmarks. There are certain things about this that are analytically derived though. For example, you'll do more of this and you'll probably do that derivation in fluids too, by the way. So for now, just know that all of these numbers in the turbulent section have a big asterisk beside them, and they vary a lot depending on the actual geometry. This is a very complicated phenomenon. Yes, please.
But the laminar could be
Assuming it's smooth, but even for turbulence happens so I want to say randomly or erratically that even for like you have to assume it's very, very smooth, like impractically smooth, in order to get this. So if you're studying a new surface, you'll have to characterize that. Does that answer your question? So if you have a rough surface, a laminar boundary layer, I wouldn't say this applies. Okay, so we have high velocity gradients in a turbulent boundary layer, which produces high viscous force. So for the turbulent case, non-smooth geometry. For example, in turbulent flow studies, they use something called like a tripwire or a trip. So, for example, a trip, and change these values. Okay, so I'm going to show you an example now of what a turbulent boundary layer looks like, and you'll understand where I'm coming from when I say it's very complicated. The laminar boundary layer is a very, very ideal case. I just want to make another point. This figure here is not to scale. If I was to draw this to scale, the laminar boundary layer would be like a very, very small portion of the growth along this plate. The turbulent boundary layer by far is the most dominant boundary layer you would get on this, okay? So this is a study that some people did in a water tunnel, developing turbulent boundary layer on a flat plate. So this is the experimental apparatus they have. They have like a really long object, and they tow it through a super long tank of water. They just tow this object through, and then they just watch one window in the water tank. So this is kind of a window here, but they're towing it along. So this is equivalent to if they were to have a really long see-through water tank and just have a camera pointed and follow it like that. But instead of doing that, you can just watch a point and tow it by. It's just kind of a relative perspective thing. So this is like if you had, say you have a fixed apparatus and you say like this table, you're just gonna blow wind over it or something. And you start here and you start looking along the boundary layer to watch the thickness. This is equivalent to that. So now instead you're just going to watch a fixed position and move the table. But this is much easier to do experimentally. So let's see what this looks like. So that shows you the scale of what we're looking at. So again, what I mentioned about trips, that's if you're studying a turbulent boundary layer, you want to produce the turbulent boundary layer. So you have a 1 millimeter diameter, so a super small wire is enough to cause that transition to turbulence. So above that, I don't even know how much of this plate would have a laminar boundary layer. It's probably just like the very front of it. Above that, it's kind of transitional, but this trip it causes it to switch into a turbulent boundary layer. So it gives you that everything's really smooth and nice. The transition to turbulence happens later. But if you cause turbulence, because of the physics of it, if you cause a small disturbance, it'll just keep producing further disturbances. So that's what you do when you basically trip a fluid like this. And so they're injecting dye through a slit behind where they trip this. So we see the turbulent motions in this. So this is what a turbulent boundary layer looks like. It's very complicated, but the majority of vehicles have to deal with this turbulent boundary layer, so we want to characterize that. Okay, so here's kind of a pop quiz. So they run this at 1 Reynolds number here. Then they're going to go to a higher Reynolds number. So for the same position, what do we expect to happen to the boundary layer? I said this at the beginning of the lecture if you want to, you can look at your notes. But for the same position, what do you expect to happen to the boundary layer if we increase the Reynolds number? Yes, please? It's going to be smaller, exactly. So that growth, see it's a little thinner? They do a comparison after this. So the higher Reynolds number, you can notice like the little vortices, they're a little bit smaller. So they take a longer time to grow. Don't worry about what RE tau means there at the bottom. You can think this of just looking along the boundary layer. So, okay, the top one is the low Reynolds number case. The bottom was the high Reynolds number. So we expect for the same exposition, which is what we're looking at, the boundary layer to be thinner for the bottom case because it has a higher Reynolds number, which is what we can see here. You'll notice like the turbulent motions look different too. This is an entire field of research in fluid mechanics, basically. Yes, you have a question, please?
Well, you're saying the boundary layer will be thinner, but how does it affect like actual turbulence? Does it get like less turbulent or more turbulent?
Flow becomes more turbulent the higher Reynolds number you have. So the Reynolds number affects at a very low Reynolds number. There's no turbulence at all. That's when basically you have a laminar boundary layer. As you start increasing that Reynolds number, the effect of disturbances in the flow gets higher and higher to a point where it will transition to becoming a turbulent flow. And it'll keep happening. See that turbulent motions, the smallest turbulent motions in a high Reynolds number are smaller, like if you look at those different motions. So the higher Reynolds number, they vary the Reynolds number in this case by basically varying u infinity. So see this plate velocity of 0.9 versus plate velocity of 0.22. That's like our u infinity. So they produce the low Reynolds number case by basically a slower towing speed. So the effective Reynolds number on turbulence is a very complicated question, but it's a really good question. Yes.
Does the rate at which the Reynolds number increase have an effect on the boundary?
The rate at which the Reynolds number increases? You mean like along the plate?
Yeah.
So in this case, the Reynolds number here, I'm not sure if this is Reynolds equivalent to Reynolds number of x, but in our case, we're using Reynolds number based on x. So it increases just linearly along x, assuming that rho, u infinity, and mu are the same, which they are, right? So the rate of increase, the slope of that is just given by rho, u infinity over mu, right? So the rate of that increase would be the same. Yes, please.
In the Couette flow, with moving opposite boundaries.
It was Couette flow. So Couette flow is what we studied last lecture, and that's like a very specific case of fluid motion. This is a much more general. This is usually what happens. Couette flow, in order to actually produce that linear velocity profile for a real flow, your plate has to be like there, like very thin gap, and you can't tow it too fast or else you'll induce this turbulence. So Couette flow is basically used as a very convenient type of flow to study shear stress and viscosity in a fluid. But most of the time you can't assume you have Couette flow. Like I said last time, if we had Couette flow every time we put something in a fluid, then a lot of fluid mechanics people would be out of business, because this is what keeps us in business most of the time. Is this is quite complex, but this is what creates like drag on airplanes, for example. So we have to understand this. Yep.
So just said that as we increase Reynolds number, boundary layer gets thinner.
Yep.
This
So
the last graph you make show it increasing Reynolds number.
that's for a fixed x. So for a fixed x location, if you increase Reynolds number, your boundary layer will be thinner. So the plot that I showed was sort of for a growth along. So this plot is about the growth of a boundary layer. So we're not looking at a fixed x anymore. So we're allowing x to vary. So if you fix all the other quantities, say you fix your rho, u infinity, and your mu. So you fix rho, u infinity, and mu. This is basically kind of like a non-dimensional x then. So you're watching the boundary layer grow. Does that make sense? Any other questions? Any other questions about this? It's quite complicated, so we'll probably extend into like Friday's lecture talking about boundary layers, because it's probably one of the more practical things. These are produced like there's a lot of science behind boundary layers, design of surfaces to reduce boundary layer drag. So I'm gonna do this example here, but we'll continue talking about boundary layers in Friday's lecture. So here's an example. We're actually going to put some numbers to the above relations. So for example, calculate the local Reynolds number, the local boundary layer thickness, and the local skin friction coefficient for flow over a flat plate. Over a flat plate at x is 1 centimeter. Then I'll give you the free stream velocity that is moving at. So u infinity is 0.1 meters per second. Mu is 10 to the negative 4 pascals times seconds. And rho is, say, 1,000. Okay. This is really just plugging into the above formulas. So the Reynolds number is rho u infinity x over mu. That's 1,000 times 0.1 meters per second times 0.01 meters. This gives us a local Reynolds number of 10 to the 4. Remember, the Reynolds number tells us, roughly speaking, if we're in a laminar or turbulent regime. So that 10 to the 4, based on this answer, based on the plot I gave above, can someone answer whether we have a laminar or turbulent boundary layer at this location? So the Reynolds number is 10 to the 4. Calculate it there. Yes, please. Laminar, good, yes. So the answer is laminar. So the 10 to the 4 means, assuming this is a very smooth flat plate, we have a triplet flow, whole bunch, there's almost no turbulence in the free stream, that sort of thing. It means we have a laminar boundary layer at 1 centimeter along this plate. Okay, so since it's laminar, we're going to use the laminar relations. So delta of x is 4.91 x over the square root of the Reynolds number, which is 4.91 times 10 to the negative 4. sorry, that's Reynolds number of x to the 1/2. Okay, then the skin friction coefficient there, 0.664 over So this is just plugging in the values. Once we calculate the Reynolds number, we know whether to use laminar or turbulent formulas. And then from there, you've already calculated the Reynolds number, so you can just plug that right into the equation. In our case, since we assumed it was laminar based on the Reynolds number, we use laminar relations. So any questions about that example? So we made a guess that this boundary layer was laminar based on the Reynolds number that we calculated. Sorry, we made a guess that this boundary layer was laminar at the x location we're trying to evaluate at. And that's a good guess because we assumed a smooth flat plate, and we know where transition happens for a smooth flat plate. Say we were to trip this flow upstream of this, and instead we're going to pretend, okay, we think we're going to have a turbulent boundary layer there. If we assume a turbulent boundary layer, we use a different skin friction coefficient formula. So that's the one that was 0.027 over the Reynolds number to the power of 1/7. So 10 to the 4 to the 1/7. If you were to assume this is turbulent, which may or may not be a good assumption, I would say in this case, you assumed it's a smooth flat plate to start, and you know where transition happens for that, you can assume it's laminar. I'm just doing this as kind of an experiment with the numbers. So if you knew that it was turbulent there because of some other information, skin friction coefficient is higher, which means that there's higher viscous forces in the turbulent boundary layer compared to the laminar, which is what we saw above. So any questions on that example? I just did the turbulent one there just to show that there's higher skin friction in a turbulent boundary layer versus a laminar boundary layer. But you should determine whether the boundary layer is laminar or turbulent based on the Reynolds number and an assumption about smooth flat plate, given no other data. Any questions? Okay, we're going to continue boundary layers on Friday. Thanks, everyone.